Okay, so last time we discussed electric charge and electric forces. Okay, there are two types of charges, positive and negative, and then there are forces between them. Like charges repel, unlike charges attract. Right. We also learned a law, Coulomb's law, to calculate the force between them. So when we use Coulomb's law, we always do it in two steps. Right? First, you use this equation, make everything positive, you find the magnitude of the force, right? Because the charges can be both positive and negative, and you make everything positive, you put all the numbers in, you calculate the magnitude of the force, then you use the effect, use the signs of these two charges. If there are two charges, you want to find out the force between them. You use the sign of the charges to figure out the direction of the forces, right? You can draw the direction of these forces. And then if you really want to specify the direction, you would pick a reference axis and use an angle between the force and the reference axis to specify the direction. So that's what we do in physics, right? So, and then we did some practice last time, but that was all about two charges, right? What if there are more than two charges? So that's what we want to do today. So let's take a look at this question, still the first PowerPoint, slide 11. Let's take a look at this question. Okay, so now there are three charges, right? We call them A, B, and C. Okay. All right, so A is positive, B negative, C positive. Now, QA, we know the amount of charge they carry. Positive 1.3 nanocoulombs. QB, negative 1.3 nanocoulombs. And again, QC, it's going to be 2.8 nanocoulombs. So we want to find a net force on QA, right? We also know that some distances here. So this is 1 centimeter. This is also 1 centimeter. Now we want to find the net force on QA, okay? So in this case, the A is going to feel a force from B and another force from C, right? So it's going to feel two forces. And then how do you find the net force? You're going to add these two forces, but as vectors, right? So when you work with vectors, you should be very careful. They have magnitude and the direction. Okay, so what you should do is this. So first, you figure out the force between A and B. So B has a force on A. So how do you find out that force? You're going to do, first you can use Coulomb's law to find magnitude, right? KE, QA, QB over RAB squared. Okay, we have all the numbers here, plug them in, you can find the magnitude. Okay, so that's the magnitude. You also need to figure out the direction, because remember, you need to add these two forces as vectors. You do need to know their directions. So the direction of the force from B on A, so you're going to draw an arrow. You're going to draw an arrow on A. You don't draw an arrow on B, okay, because we are focusing on the force on A, right? It comes from B, but it's on A. So I'm going to draw an arrow here starting on A, okay? And how do I know the direction of that arrow? You're going to take a look at the signs, right? That's what we just said. If they carry positive charge, they carry the same type of charge, the force is repulsive. If they carry opposite charges, the force is going to be attractive, right? That's going to help you figure out how you're going to draw that arrow. Okay, so that's going to be the force between A and B. Okay, magnitude, direction, you draw an arrow. Then you're going to repeat the same process with A and C. This is A. This is C. Forget about B. I'm just interested in the force between A and C. Now the force between A and C, first of all, you can calculate the magnitude. Coulomb's law. Right. A and C. And now this we know all the numbers, right? QA, QC, and the distance. Of course, it's going to be 2 centimeters now. You can convert it to meters. Everything SI units, right? You will also get a number, okay? But once you get this number, you're going to also draw an arrow on A. You don't draw an arrow on C because you want the force from C on A. You're focusing on A. You want to find all the forces on A, right? I know that A also has a force on C. And they must be equal and opposite, right? That's Newton's third law. Everything's consistent. Their action and reaction, okay? But I want to find all the forces on A. So I don't want to draw the force on C, even though I can, okay? And it's easy once I have the force from C on A. But I'm going to draw an arrow on A to present the force from C on A. Again, how do I draw that arrow? How do I know the direction of that arrow? Take a look at the signs, right? Like charges repel, unlike charges attract. Okay, they both carry positive charges, right? Is the force going to be repulsive or attractive? How would you draw the arrow on A to represent the force from C on A? Okay, so that's going to be the next step. Once you have these two numbers, these two arrows, and because these two forces, they're going to be along the same line. So you're just going to add or subtract them depending on the directions, right? We know that even intuitively, if they're in the same direction, you add them. If they're in opposite directions, you subtract them, right? Okay? So that's what we're going to do. So once you pause the video, find these two numbers, draw these two arrows, and then you're going to figure out if you're going to add or subtract them to get the magnitude and the direction of the net force on A. Okay? All right, so let's see. What are the numbers I got? So first of all, I put numbers in this equation, QA, QB, right? You convert nanocoulombs to coulombs, centimeters to meters. Don't forget the square, and K is a constant. So this number I got, 15.21 times 10 to the negative fifth newtons. Okay, that's the magnitude. What is the direction? Okay, so let's take a look at these two charges. B is going to attract A, right? Because they carry opposite charges. Okay, so if I would want to draw a force, draw an arrow to represent a force from B on A, right? B is going to pull A toward A. Okay, so B is going to have a force on A in that direction. That's attractive, right? B wants to pull A closer. Okay, so this force is going to be to the right. Now you do the same thing for the force from C on A. Put all the numbers in, distance 2 centimeters. This number I got is 8.19 times 10 to the negative fifth newtons. Okay? Now what is the direction of this force? Okay, take a look at the signs. A and C, both positive, force should be repulsive. So C is going to repel A. C wants to push A away. Okay, C wants to push A away, so that's the direction of the force, right? So this is the force from C on A. So that's how I would draw that force. All right, so now I do have the direction for that force to the left. All right, you see that A feels two forces. One to the left, one to the right. Of course, the net force is going to be a difference. It's going to be the difference between these two forces, right? So you're going to subtract them. And then you're just going to do the larger one minus the smaller one. This one's larger. This is one smaller. So the net force on A, it's going to be the larger one, B on A, minus C on A. Right? Subtract them because they are in opposite directions. When you subtract them, you should get 7.02 times 10 to the negative fifth newtons. All right? So that's going to be magnitude. What's the direction? Which one's larger? This one's larger. So this one is going to wing out, right? So the net force is just going to be in this direction, okay? To the right. So this is the net force on A, right? It's going to feel a force 7.02 times 10 to the negative 5th newtons to the right. So that's how you find the net force on one of charges if you have a group of many charges, right? And of course, you can repeat this process if you have 4, 5, right? As long as they are along the same line, you're just going to add or subtract, okay? You just, so that's when they're along the same line, right? But if they are not along the same line, okay, so you would have arrows this direction, this direction, this direction, that direction. So you can't just add or subtract them, right? So you have vectors in this arbitrary direction. What do you do? How do you add them as vectors? That's also what we learned in Physics 1, right? Vector analysis. You can only add or subtract components, okay? So you're going to find the components of each vector, x and y, right, or z. But we're not going to go to 3 dimensions in this class. So we're just going to do x components, add it together, y components, add it together. That's going to be the x component for the net force, y component for the net force. And once you have these two components, you combine them using trig to find the net force, the magnitude, and the direction, okay? So of course, in this case, when we specify direction, we would pick a reference axis and then use the angle between the vector and the axis, right? That's how we specify a direction for vector, arbitrary vector in physics, right? We don't describe that using words, okay? We describe that using an angle and a reference axis. That's very accurate, okay? So that's what we're going to do next. So let's practice that. The next question. Now we have 3 charges. They're not along the same line. They don't lie on the same axis, right? So we're going to do vector analysis. So let's draw it out. So 3 charges, Q1, Q2, so this guy is called Q1, Q2, Q3, all right. Now we know the charges, right? Q1 is 3 microcoulombs, Q2 negative 2 microcoulombs, and then Q3 5 microcoulombs, okay? Of course, microcoulombs, you can convert it to coulombs. And then we also know they form a right triangle, okay? So that makes our life a little bit easier. And then these 2 sides, okay, so I should make them like almost the same length. Okay, so this is Q1, okay? So this side is A, this side is also A, okay? And we also know A is 0.1 meter from the problem. So of course, if you connect these 2 charges, that's the hypotenuse of this right triangle, right? So that's going to be square root of A if you use a Pythagorean theorem, okay? Now we want to find the net force on which charge? On Q3. So we want to find this charge. Okay, first of all, I know there should be 2 forces on Q3, right? Q1 has a force on it. Q2 has a force on it. On Q1 also has a force on it. So what I'm going to do is this, right? I'm going to first find these 2 magnitudes. Okay, finding these 2 magnitudes, that's going to be easy. You're going to do 1 on 3. You're going to do KE, right? Q1, Q3 over R13 squared. So R13 is this length. And then you're going to do the force from 2 on 3 KE Q2 Q3 over R23 squared. But you can't just add or subtract these 2 numbers, right? Because let's draw these 2 arrows so we know the direction, right? So the force from 2 on 3, okay? So let's take a look at 2 on 3. They carry up the charges, so the force between them should be attractive. So attractive, and I want to draw the force from 2 on 3, so I would draw an arrow on 3, Q3. I don't draw an arrow on Q2. So Q2 is going to attract Q3. So that means it's going to pull Q3 a little bit closer, right? So that's going to be the force. Okay, so that's the force from 2 on 3. So that's horizontal, okay? Now what about the force from 1 on 3? Well, in that case, first of all, they both carry positive charge, right? So it's going to be repulsive. So Q1 is going to repel Q3 in that direction. So this is how you're going to draw that arrow, right? So that's the force from 1 on 3, okay? So, and then this is not horizontal or vertical, right? And then if you want to add these two vectors together, you can just add numbers, right? The magnitude. What you should do is this, right? That's what we learned in physics 1. You're going to break this guy into x and y components. Okay, using trig. You're going to do the same thing for 2 on 3, x and y components, right? And of course, in this case, if you still use the normal x and normal y, right, I still call these x vertical, y horizontal x, and positive to the right, positive up. So the 2 on 3 only has an x component, right? So it doesn't have any y component. That's going to be 0. But you still need to break the force from 1 on 3 into x and y, right? After you find these 4 numbers, we already got one. So what are you going to do with this, right? So you're going to add, so the net force is going to have also an x component and y component, right? So the x component is going to be y 1 on 3x plus 2 on 3x, right? And then the net force on 3y component is going to be 1 on 3y plus 2 on 3y, right? So you will get 2 numbers. That's going to be the x and y components of the net force. Then you're going to combine them to find the net force, right? So you're going to still find the magnitude and direction of the net force. So then you're going to again draw the diagram, draw these 2 components. Say, okay, so now I don't know the components I would get, right? So let's just assume, say, but the rules are the same, right? Say I get an x component at the end in this way, y component in this way. So this is the net force x component, net force y component, right? So what is the net force? First of all, we know how to draw that, right? Pictorially. This, it's going to be the net force. Okay, so this is the net force on 3, right? And then how do you specify that force? I would find the magnitude by using x squared plus y squared and square root, right? Still Pythagorean theorem. And the direction, I would pick a reference axis and an angle to tell you, right? In this case, if this is these are the 2 components I get, I would just say, I can calculate this angle for you, theta angle, and say, like 20 degrees, okay, it has an angle 20 degrees above this positive x direction, okay? And the magnitude, say, like 10 newtons. I give you these 2 numbers, you know all the information about this net force, right? So that's how we find the net force, all right? So it's still vector analysis, right? We're working with vectors, components, we do trig, okay? We're gonna break each vector into x and y components. They add all these components and then use the x and y components of the net force, go backwards, find the magnitude and direction of the net force, okay? So it's going to be many steps. I want you to pause the video, do the algebra, combine the components, and then find the magnitude and direction of the net force, okay? And see if you can find the right answer. All right, okay, so let's see what are the numbers I got. So let's see. So this number, okay, you put all the numbers in, right? KE constant, Q1, Q3 given, right? And then the distance between them is going to be square root times 8.1 meter, okay? So this number I got is 6.75 newtons, okay? So that means this force is 6.75, but I do need to break it into x and y, right? So I'm going to draw the axis here. This is going to be the x. This is going to be the y, right? So how do you find the components? This is how you're going to find the components, right? You still draw these right triangles. This side, it's going to be the x component, and this side is going to be the y component, right? Okay. So, and then you can find these components. Well, first of all, you know the magnitude, right? Then you just need an angle, right? You can use any angle, okay, that's in this diagram, right? For example, this is an easy one because these two sides, in this big right triangle, these two sides are equal. So this is 45 degrees, 45 degrees. So this angle must be also 45 degrees. And this is also 45, right? So you can use either angle, okay? Now, and then we can find it. So 1 on 3 x is going to be the hypotenuse, 6.75 newtons times, okay, if I want to find this side and then I know this angle is 45, that's going to be cosine, right? Because this is adjacent to 45. All right? So in this case, I would get, the number I got is 4.77 newtons. And then take a look at the direction of the x component to the right. I equal the right positive. So this component is going to be positive 4.77 newtons, right? If I get a component in that direction, the number is still going to be 4.77, right? But when I write it in component form, I need a negative sign, right? That's how we distinguish left and right, up and down in physics, right? Because we can't plug words in to the left, to the right, up and down. We use signs to distinguish them. So y component, 6.75 newtons times sine, because y component is this side, which is also this side. So that's opposite to 45, right? So that's also going to be 4.77 newtons, because sine, cosine 45 are the same. So this is also going to be 4.77 newtons, okay? So as I said many times in physics 1, you don't need to memorize x is always cosine, y is always sine. It totally depends on what angle you get, right? For example, in this case, okay, sine and cosine 45 is going to be the same, so it doesn't really matter. But if I know this angle from the problem, or if I find this angle using some information in the problem, so then, you know, everything's going to be reversed, right? Cosine becomes sine, sine becomes cosine. You just draw these diagrams, okay? You don't need to remember shortcut. That's not what we're doing in physics. I emphasize many times. Physics is not about memorizing shortcuts. So I can just, when I see a problem, I just plug numbers into the shortcut, okay? Draw this diagram. Use the definition of sine, cosine, tangent, so you know what to do, right? Of course, you need to be very good at this trick, okay? All right? So again, the y component is also up, so the value is this, and then I'm going to call it positive, right? If I draw these components, I get the y component down, the value is going to be this. I'm going to assign a negative sign, okay, to indicate it's down, not up, okay? All right, so these are the x and y components for F13. Now F23. First of all, find the magnitude. Q2, Q3, distance is 0.1 meter, right? Now put all the numbers in. This number I got is 9 newtons, okay? And this number is 9 newtons. So, and then in this case, you see, we already figured that y component is 0, because it doesn't have any y component. It's totally in horizontal direction, but it's in, to the left, it's in the negative x direction, right? So when I write this in component form, I should say this is negative 9 newtons, So I don't need to write 9 newtons to the left, right? I'm just going to say negative 9 newtons, okay? Then I'm going to add the components, right? Now I can add them or subtract them, right? Well, we add all these components, right? After we assign them the correct signs. X component, you're going to add this guy and this guy together, right? Keep the negative signs, don't drop negative signs. Okay, a lot of people, they just freak out when they see negative signs, they erase negative signs. Don't do that. Negative signs in physics, they're meaningful. They're telling you something. Don't erase them. You add these two components together, you will still get a negative sign. Okay? You didn't do anything wrong. It's just telling you the X component is in that way. It's not in this way. Okay? Alright? Now, then add all these Y components together. Well, that's easy because this guy plus 0 is going to be itself. Okay? So that means I get an X component this way, but Y component is still positive. So this diagram was wrong, right? Well, because we didn't know the direction of these two components, we will get. Right? So actually, the right diagram is going to be this. So I get a X component in this direction. I get a Y component up. Right? So this is a net X. This is net Y. Right? So how do I find the net force? This, it's going to be how I draw the net force, right? So this is the net force. I'm going to draw it a little bit nicer. Okay? So, okay, once you have these two components, you can find out the magnitude and the direction, right? Magnitude, you just do X component, X squared plus Y squared, and then square root, right? Still Pythagorean theorem. All right, so this number I got, it's going to be 6.38 newtons. So that's the magnitude of the force, net force, Q3 fields. Q3 field, the force 6.38 newtons, right? What about the direction, okay? The direction, okay, it's in that direction, okay? But how do you describe it in physics, okay? We will pick a reference axis and then tell you the angle between the reference axis and the director, right? In this case, I would just pick this one. Or you can pick this one, right? If it's a free response question, you can pick any axis you like. Just let me know what you mean, right? As long as I know what you mean, you got it right, okay? So if I pick that one, the theta angle, it's going to be tangent inverse. Okay, I'm working with this right triangle, so I don't need to worry about the signs because I just want to figure out this angle, right? So it's going to be this side, which is the length of this Y component. 4.77 newtons. Okay, what about this side? The length is 4.23 newtons, right? The sign is just is telling me the direction. I already know the direction. I drew the direction, right? So now I'm working with this right triangle. I want to figure out then the angle, an angle in this right triangle. I'm just gonna use the magnitude of each side, right? So this angle, and again, tangent inverse, is it always y over x? Don't remember that, okay? You draw it out, you're gonna see, pick an angle you want to find. You're gonna see if you're gonna use y over x or x over y. It can change, right? Okay? And this angle I got is 48 degrees, all right? So this is how we find the magnitude and direction of the force, right? So if you want me to tell you the force, right, I can tell you the Q3 feel the force 6.38 newtons, and direction of the force is going to be 48 degrees above negative x axis. And if I tell you that information, you know everything about this vector. You can draw it out yourself, right? Okay, very clear, very accurate. That's how we do things in physics. okay? All right, so this is a very good problem. It reviews vector analysis and also with this Coulomb. So this is the only new thing we learned in this part, right? Everything else, vector analysis, that's what we have already done in Physics 1, okay? We're still, in this class, we're still gonna use a lot of the concepts, okay, skills and techniques we learned in Physics 1, okay? That's what I said. All right, and that's gonna be the rule, right? That's gonna be the rules if you want to find the net force of one single charge in a group of many charges, right? So you just need to repeat this process, right? So if you go beyond 3, right, 4, 5, right, you just repeat the same process, right? For example, if I have 5 charges, 1, 2, 3, 4, 5, right? This is Q1 positive, Q2 negative, Q3 positive, Q4 negative, and then Q5 is positive. I want you to find the net force on Q5. Well, okay, draw the force from 1 on 5, repulsive, right? Draw the force from 2 on 5, attractive. Draw the force from 3 on 5, repulsive. Draw the force from 4 on 5, attractive. Okay, you got 4 vectors. Break each vector into x and y. Add all these x components together. Add all these y components together. Okay? At the end, you will get a net x component for net force, y component for net force. Okay? Combine them using trig to get the magnitude of net force and the direction. Right? And direction, in most cases, we're just going to specify that using an angle with respect to a reference axis. Okay? So you can generalize to your 100, 1,000 charges, right? If you give me a problem with 100 charges, I want you to find the force, net force on Q35, okay? You may hate me, okay? But you can still do that, right? It's gonna be a lot of work, but if I give you 1 day, you should be able to do that, right? Carefully, okay? It's gonna take you a lot of time, okay? So that's the theory, right? So I'm done with this type of question, right? You can give me like, like 100 different problems, just like different combinations of charges, different distances, okay, charges, whatever. I'm going to use the same theory to find a net force on one of the charge, right? I'm just going to repeat the same process, okay? Pair it up with every other charge. Okay, find the vector, break them into components, add components together, combine them to find the net force, okay? So we're done with this type of question, okay? If you want to find the electric force on any charge in a group of point charges, that's how we do that, okay? But it's going to be tedious, right? It's going to take a lot of time, right? So as physicists, we always want to find an easier way to do algebra, right? Sometimes you can find an easy way to do that, okay? Which is nice, okay? Sometimes you cannot. You would just have to use the fundamental theory, do the hard work. So in this case, yes, there is an easier way to calculate the force on a single charge from a group of charges, point charges, okay, with the introduction of a new concept called electric field, okay? So with this new concept, calculating electric force on a single charge from a bunch of other charges is going to be easier than just using coulombs or repeating coulombs or between for every pair in this group, okay? But you still need to calculate the electric field, this new concept we will introduce, okay? So calculating electric field, this new concept, can be very hard, okay? So that's what we're gonna do next. But once you have done that work, calculating the electric force, it's going to become very easy. And then if you want to repeat the same calculation with different point charges, okay, so that's going to save us a lot of time, okay, by introducing the new concept, electric field, Okay, and then in addition, electric field is a very useful, very important concept in physics. Okay, without that, you cannot unify electric force and magnetic force. You cannot predict. You wouldn't be able to predict EM waves. Okay, that's what we're going to see at the end of the class. Okay, so that's what we're going to do next. Next time, we're going to introduce this new concept, electric field, and we're going to define that. We're going to see how it's connected to electric force, and then how it's going to help us calculate the electric force, okay, a little bit easier, okay? So I'm going to stop here for this video.